Bismillahirrahmanirrahim. Welcome to Diode and Application Season 2, of course brought to you by Islan. Let's talk about the topic we are going to discuss today. I selected two topics for us today, and this is the step recovery diode. Very precisely we will discuss, because this is not a very important type, and the tunnel diode, and then of course its application, and this will be probably the third last video of the second last video of the diode types. Then we will try to move forward on the troubleshooting episodes and try to wind up this season 2. And this is the packing. You can see that this type of the package available, and this is mostly you found in your TV circuit boards, and normally not in the LED type TVs, in the old TVs in which the cathode ray oscilloscope type display is used, and in that this is used for the very high frequency band tuning. Whenever if you tune your TV using your remote, you see that there are three bands. That is very low frequency tuning first band, then very high frequency tuning band, and that is this band that is used by this IC. So and the last band, ultra high frequency band. This is the simple look like. Also in this type of packing is also available and step recovery diode. And there is another packing that is same like the previous, but just the representation and the look is different, depend upon the space available. And this is the little bit you can say that newer variant of the last diagram, and this is the different representations. And the one type of the step recovery diode SRD, and this is another representation, and both are used. And here you can see that this is a general diode symbols, LED symbols, just very simple. For example, here just arrowhead symbols are direction is different, opposite direction, and the diode is changed from LED to photo. So these are the different symbols. You must not confused about these symbols. We had already discussed. These are the different types of the LEDs or pin diode, step recovery diode, Zener diode, tunnel diode, vector diode, so on. We almost discussed every. Just this gun diode we had not discussed so far. We will try to discuss and cover up most of the diode. I tried to, basically the idea behind the season 2 is this, to cover up the most of the diodes that are used in the everyday life, and to discuss their purpose, their application, and their working principle very precisely. So I'm trying to cover most of the diodes. The step recovery diode, the main thing here is the graded doping. The main point to be noted here is the graded doping. Means to say the doping level is different for the different regions, or you can see that the doping is different for the certain conditions and different for another conditions. So where the doping level of the semiconductor material is reduced as the p-n junction is approached. When the p-n junction or a depletion region between the p-n junction is created, that this is doping is semiconductor material is reduced, doping level is reduced of the semiconductor. This produces an abrupt change, very fastly change, that is the off time, by allowing a fast release of the stored charged. And when the fast release of the stored charge means to say that all the minority carriers stored in the depletion region, like in the normal diode of the p-n junction diode, when there are a few minority carriers that are the cause of the reverse current, when they are released here in this case, like the step recovery diode, if they are released very fastly and very abruptly, this means that they're off when diode goes in the off state very fastly. And it also allows a rapid re-establishment of the forward current, which means their turn on time is also very small. So this diode can be used in the tuning circuits, as well as the low oscillators, fast on-off switches, as well as mostly their application depends on the frequency synthesizer, frequency multipliers, very high frequency, so on, depend upon the frequencies application. The second diode we are going to discuss is the tunnel diode. The tunnel diode exhibits a very special characteristic known as the negative resistance. Negative resistance we already discussed in the pin diodes previous episode in the electronics. Negative resistance is represented by NR. N stands for negative, R for resistance, is a property of the some electrical circuits and devices in which an increase in the voltage, decrease in the current. So this is called the inverse relation between the voltage and current, can be calculated from the Ohm's law. V is equals to IR. For example, R is equals to V over I. When R increase means increase in the voltage or decrease in the current. This is the inverse relation between the voltage and current, means negative resistance. So this is the forward voltage of when the tuner diode is connected in the forward bias. When the anode is connected with the positive and cathode is connected with the negative terminal, then the current is increasing, let's say, towards the y-axis, and the along horizontal axis voltage is increasing towards the right side. Then this diode basically start conducting even below the 0.7 voltage drop, like in the normal diode. This diode act as a just like you can say that ohmic contact, or just like a metal piece. When we for example we apply current voltage to a metal wire, the current starts to flow without any resistance. But here, when it reaches to a at this point, at a certain point, then it's going to decrease gradually, and then after another point is reached, this is going to start once again like a normal diode. But what happens, this is the new scenario, and we will discuss this. And this, from this point to this point, this is called the negative resistance and negative differential resistance region. So this is the different types of the tuner diodes packing available. This is most widely, this is the zoom picture of this one, is the another. So this is the different books uses different types of the two symbols. Some books use the normal diode, and in a subscript there is another curved type line. But here some books uses no in subscript, but here they use this type of just bent here at the end. So this is the most widely used, but this is also used in some books, old books or new books also. Anode and cathode representation is very simple here. The tuner diodes are constructed with same germanium or silicon, silicon, germanium or germanium arsenide. But the main thing here is they are more heavily doped. Not only doping, but the more heavily doped than the conventional rectified diode. What happened as a result? As a result, the heavily doping causes the extremely narrow depletion region. This is, please note this is the extremely narrow depletion region. This is here, you may found it large depletion region, wide depletion region, but this is for understanding. It is very narrow, and a p-type region, just like a normal diode that we had discussed in the season 1. P-N junction diode, p-type is doped with the majority charge carriers, holes, and some minority carriers also available as electrons, while in the N region some majority carriers are the electrons, some holes are also available as a minority carrier. So in this diode, this is also called a minority carrier device, because in this both type of the charges available, working principle depends upon the electron as well as holes. So these type of the diodes are called the minority carrier diodes. The heavily doping allows conduction for all the reverse voltages, so that there is no breakdown effect with the conventional rectifier diode. You can see that the normal diode does not allow the current to flow in the reverse direction, but here you can see that it allows current to flow, and almost no breakdown effect, because there is no blockage. So if there is no blockage, no limits. So if there is no limit, so it cannot be reached, so there is no breakdown. So that's why it looks like no resistance even in the reverse bias, and even in forward bias there is no resistance, just like a simple wire where we apply the voltage and current is received. In forward bias same, but there is a difference. I will try to discuss in the next slide. Here, extremely narrow depletion region permits electrons to tunnel through the p-n junction. This is the p-n junction. It allows current to flow. Very low forward voltage, bias voltage, and current act as a diode act as a conductor, and it allows current to flow. And this is the tunneling current. This current here under this curve area is called the tunneling current. This is then at point B, the forward voltage begin to develop. This forward voltage increases at point B here. After point B, this voltage is now enough to create a barrier potential. This creates a barrier for the current to, and now current is going to decrease till point C. This is called the negative region, and we can calculate the slope of the negative resistance using the Ohm's law, R is equals to V over I. But here the V is changing and current is changing. V can be calculated from point B. If you move along the towards horizontal axis and touch this point to this line, then we can calculate from this point C minus B is called the delta V. Same if we go along point C and point B towards the I, that is the Y axis, we can calculate easily delta IF, and so we can easily calculate these things. The effect is the effect is opposite to that is described in Ohm's law, where an increase in voltage results in increase in the current. Definitely this is an opposite effect. We had already discussed that increase in a voltage is decrease in the current. At point C, the diode begins to act as a conventional forward bias diode. After the points this point C, the diode will start to behave like a normal diode. A parallel resonant circuit that is shown in the here diagram, that is consists of the RLC, resistance, inductor and capacitor. When the switch is closed, the input parallel equivalence of the series winding resistance of the coil RP, this is the coil resistance RP, when the tank circuit is shocked into the oscillation by the application of the voltage or damped sinusoidal output, this results when the sinusoidal input, for example this is the sinusoidal input is connected, the output due to damping, the result is the attenuation and degradation of the signal until it reaches to point 0, and this is why this communication is seriously damaged due to the damping, and this is because of the resistance of the tank, that is the resistance of the tank internal, and which prevents the sustained oscillation, because energy is lost when there is current through the resistance. This is because the negative resistance characteristics we can, if we use this, is very helpful here in this case, because when here the resistance is when their value is decreasing, their peak point value is decreasing, for example voltage is decreasing, then current is increasing. So this is a reverse effect. For example, in the previous slide here, if I try to show you from here this slide, here if it is decreasing, their magnitude is decreasing, then its other aspect, for example if current is decreasing, then voltage is increasing, so it tries to maintain the constant output. This is because of the negative resistance characteristic of the tunnel diode contracts the positive resistance characteristic of the tank resistance. The tunnel diode is only used at a very high frequencies. The main thing is you have to remain in this region. If you go into this region, then this will act as a normal diode and it will have no effect on the circuit. To connect, this is the diagram, you have to connect this diode in this series tunnel diode, and there are the two limiting resistance as well available, and this the topic discussed next time. This is probably the next episode will be the last episode of the diode types, that is the current regulator diode. The Zener diode was the voltage regulator, and now we are going to discuss in the upcoming episode current regulator diode. So further application will be discussed, and later after the current regulator diode we will go into the troubleshooting applications. So watch, learn, grow, see you next time.